So welcome everybody. Today's colloquium speaker is Anindya Ghosh. Anindya did his PhD at the University of Iowa with Usha Malik, and then he has been a postdoc at the University of Arizona at Tucson, and mostly works at CERN essentially. Today he is going to talk about signals in the shadows, dark matter and BSM di-Higgs in ATLAS. Over to you, Anindya.
Okay. Yeah, so as Sudhir was saying that I would talk about signals and shadows. Basically my work focuses on dark matter and BSM di-Higgs searches in ATLAS experiment at the LHC. So just to give a brief introduction about myself, I did my bachelor's from Calcutta University, and then I did my master's from IT Madras. Then I did my PhD from University of Iowa, working with the ATLAS experiment, and currently now I'm a postdoc at University of Arizona since 2021. So all my research work is on ATLAS. So to go into more details about my research focus, I work on experimental high energy physics. So this is basically most of data analysis and also some developments for ATLAS detector upgrades for High-Luminosity LHC. Here I have highlighted some of the searches that I have been involved with for the physics analysis. For example, dark matter searches with the run2 dataset with ATLAS, and also the combination of all the dark matter searches in ATLAS. And then in hardware, I also contributed to the beam test for High-Luminosity LHC upgrade project during my PhD. And right now, a lot of effort is going on the software developments for High-Luminosity LHC, where I work on this project called event filter tracking, which I'll explain in later stages. So to give a rough outline of how the talk would proceed today, I'll first give a brief introduction about standard model. Then I'll talk about LHC and the ATLAS experiment. Then I'll talk about dark matter and di-Higgs. Then I'll give a rough idea about how physics analysis is performed in ATLAS. And then I'll talk about my searches on dark matter, di-Higgs with ATLAS, and what are the future prospects of this moving forward at High-Luminosity LHC. So to begin with the standard model, as you know that this is the most complete theoretical framework available to describe elementary particle physics. And the discovery of Higgs boson in 2012, it completes the model. However, as we will go forward, that there are a lot of shortcomings, but this model pretty much describes what we know so far about particle physics. There are different types of particles that it classifies. For example, you have the fermions, and then you also have the bosons, and there are different generations of leptons, quarks, and bosons. Now, so far, standard model has been very good in explaining electroweak and strong interaction. For example, it explains well Higgs mechanism and how particles get their masses. And also, so far, whatever standard model has predicted, LHC data has agreed in most cases, or we are heading towards standard model validation. However, there are a lot of limitations of standard model. For example, it does not explain dark matter, dark energy, and also there is no explanation for matter-antimatter asymmetry so far. But there are BSM clues which can give you some pathway to explore these areas. So that's why studying BSM standard model is very important in search of what's unknown in our particle physics world. And a very nice gateway to all of this is di-Higgs, which can open up a new window to new physics. So what it basically does is you have the standard model prediction that you can have di-Higgs processes. For example, as I see here, a Feynman diagram where you have these couplings between triple Higgs, for example, and the standard model predicts that these kind of processes do exist, and the predicted cross section is around 32 femtobarn at 14 TeV. Now you can see that there is a coupling constant here. You can actually measure this and see if they actually match with your standard model prediction. If not, then probably there is something else. So this is a very good avenue to also test standard model and also to see if there is something new. Now, to go ahead with how we actually test and what are the facilities available, as you know that the Large Hadron Collider is at the this is the world's largest particle accelerator. This is based at French-Swiss border, and this is basically a 27-kilometer humongous ring where you have particles colliding at around 13 TeV until 2018. and now the energy has been increased to 13.6 TeV for the current data taking period, and it will be 14 TeV in 2029. So there are 4 large detectors. You have the Atlas, where I work, then you also have the CMS detector, and you have ALICE and LHCb. So these are all taking data simultaneously and try to see if there is something new going on. So now the question is, how does the Atlas detector look like? So this is basically a diagram of the Atlas detector. You can see that this is kind of a huge detector. Its length is around 44 meters and height is 25 meters. So as a comparison, this is a scaled human size, so you can see it's humongous. There are multiple components of the detector. You have inner detector, where you have the collisions happening around this area. Then you have the electromagnetic calorimeters, so for example here. Then you have the hadronic calorimeters, and then you have the muon chambers at the very end. You also have superconducting magnet system, so that you can measure the PT and momentum, PT and charge of charged particles. And there is also something called trigger system, where basically billions of particles are colliding, and it's impossible to save them all because it will require around 60 terabytes of space per second. So you cannot physically store everything. That's why you need a trigger mechanism, so that you store only your interested physics event. Now the question is, how much data actually we have recorded, or what does that even mean, like how many events we have? So to measure the number of the data quantity, we have something called luminosity. This is a parameter which describes the rate of collision happening per unit area. And when you integrate this over a specific time period, let's say for 1 year, these are called integrated luminosity, and this is measured in inverse femtobarns. So between 2015 and 2024, Atlas, for example, has recorded 300 femtobarn proton-proton collision data. That is roughly 10 to the power 16 events. Now you can already see that this is a humongous number of events, and what we are trying to do is find, for example, Higgs boson or a new particle from among this heap of events. Now, although we have a lot of events, but the particular physics interest you are trying to see, also the number of events for those depends on the production cross section. So for example, with this 300 femtobarn total luminosity, Atlas have recorded 15 million Higgs bosons. In comparison, you have 270 million top quarks. So if you have an analysis, let's say, where you want to let's say discover Higgs boson, you have to somehow discriminate these 270 million top quarks, and on top of that you have other processes. So you are basically trying to find one object among millions of others to see if something is there. Then how do we do it? So the standard strategy in Atlas and also largely in LHC is that you have to discriminate the signal which your physics interest from the background events which you actually have already discovered. So for example, could be your top quark. The way we do it, we define these different analysis regions. So for example, you will define a signal region where you would try to maximize the signal contamination in that zone. So for example, let's say you have a heavy scalar Z prime, and the shape of the missing energy, for example, gives you distributions like this red color here, also this green color, and also this magenta color. And then you also have these backgrounds, which are your known processes. So for TT bar and Z plus Zs, these will differ in shape. So your idea is that you define these regions where you maximize that you have most signal. So for example, this is missing energy binning, and you can see that if you apply these different cuts, you can actually distinguish between your signal and background. So you define these signal regions and control regions and get these kind of distributions, on which you actually do a statistical interpretation and see that if your if you basically see an excess in data. Now most of the cases, I'm pretty sure you have heard not like a significant excess since 2012. So that is all not lost. Once you don't discover something, what we actually try to do is eliminate a model phase space that is no longer viable for a new physics in LHC. Okay, so to summarize how an experiment is performed and data analysis is done in ATLAS, I'm trying to give an overview here. So for example, you start with a physics process of your interest. You do a Monte Carlo simulation. So this is all theoretical here. So you generate your Monte Carlo using some simulation software, and this is true for signal and background. And then this is all theory Monte Carlo. You put through something called ATLAS detector simulation, where you are telling basically, okay, I have a theory that predicts that, for example, this particle will be produced with this much PT and so on. Now that is not actually always true in terms of experiment. When you measure these quantities, there will be detected inefficiencies. Some part of the detector might not work, and you will also have limitations in which region of the detector the particle falls. So maybe you will have particles flying around the detector will not be able to recognize them. So all of these imperfections and uncertainties are taken into account in this detector simulation. And this part, once you have the simulation, it goes to something called reconstruction. Now, well, I write it ATLAS here for different analysis. It would be different, for example, CMS reconstruction, LHCb, and so on. And this step is common for both the Monte Carlo and the actual LHC data. What it does is you have all the electrical signals in coming out from the detectors, and what you do is you try to reconstruct them into physics objects. Physics objects means at this stage you can actually say that this is an electron or a muon, and what are their charges, what are the PTs, masses, and so on. Once you are done with that, then you go through this analysis process, where basically that's what I showed in the last slide, that you define your different regions to distinguish between signal and background. And you will end up with some histograms where you will see how your modeling looks like. So modeling means your Monte Carlo to signal, Monte Carlo to data, and see if you have some excess there. So once you have these distributions, this goes through a statistical analysis, where basically you see if you have an excess or not, and if there is an excess, if it is statistically viable to say, okay, I have a discovery, or if there is no excess, you try to eliminate or exclude a phase space of a model you are testing. So this is kind of a whole picture of how an ATLAS or any high energy physics analysis at LHC is going on. So as you can see that there are multiple steps on here, and this is not just one single theorist or a physicist working on a specific model and comes up with a final paper. So there are a lot of engineers and a lot of computation going on, so that's why it's a collaborative effort, and it takes a lot of effort from everybody. So now coming back to my research with ATLAS, since now we have kind of set a base of how analysis is performed in ATLAS. So to start with dark matter, as you know, that it constitutes about 24% of our universe, and there are a lot of models which can predict production of dark matter. And I took this picture from Physics of Dark Universe, where they basically have simplified how you can categorize these different models. In LHC, we mostly focus on simplified dark matter models. For example, you have a Feynman diagram here. You can have a mediator. This can go to fermions or dark matter, and if you have fermions, they can also decay to dark matter candidates and so on. So what do we know about dark matter so far? So far we know that this is a weakly interacting, probably massive particle, and we do these resonance searches for mediator particles that will facilitate interaction between standard model and dark matter particles. Now why is this important? This is important because to search for something in LHC, it has to interact with the standard model particles, because the detectors can only detect if it interacts with them. However, if it is a dark matter particle, since it does not interact, it will leave the detectors a missing energy, which is a momentum imbalance, right? So what you are trying to do is you see if you have a process where you have a huge missing energy in association with something else you can measure. So let's say your final state has a Higgs boson plus a dark matter. You are expected to see a Higgs boson plus a huge amount of missing energy. So now, where is it? So as I said, that if dark matter is produced at LHC, it will leave a trace of missing energy, and you have to measure it in association with something else. So it could be Higgs boson. So I show here one of the Feynman diagrams from the 2HDM plus A model, where basically you extend your Higgs sector with another doublet, and you have all there are 5 more Higgses, for example. This capital A, small a, these are all heavy scalars. So in this case, this capital A can go to a Higgs boson, which can go to 2 B quarks, and then the small a, which is also a pseudoscalar, it can decay to dark matter candidates, these chi's. So you will not detect this. If this is produced, it will fill a missing energy, it will give a missing energy signature at your final state. So in Atlas, we mostly do dark matter searches in terms of interpreting with a specific model. For this case, we mostly use 2HDM plus A. This is vastly has been tested at LHC, and this was also my thesis, that I did mono Higgs searches with dark matter searches with mono Higgs, where you have a Higgs to BB and missing energy. Again, here you don't find any missing, a significant amount of missing energy, then you partially, or you can also fully exclude the model if you are sensitive enough. So now, to give a rough example of what I actually did during my thesis with the mono Higgs search. So I was doing this analysis with another student, and both of us had the same main thesis topic, but there were 5 postdocs and also faculties from each institute. So there were around 10 people, the total group. And this is our results. So for example, let's discuss about how to interpret these plots before I will explain what we observed. So these are basically, since we don't observe any excess, what we try to do is eliminate a certain phase space of your model. In our case, it was the 2HDM plus A model. And on your x-axis here, you have the m small a mass, and on the y-axis you have the capital A mass. So what we are doing is excluding the phase space of masses of these two pseudoscalars. And this black line here is what the exclusion is obtained using the actual LHC data, and the dashed one is what we expect when we don't have data. That means we don't look at the data, we look at the Monte Carlo and predict what we should observe when we actually look at data. So what this plot tells you is that all of these regions inside this curve is actually excluded. That translates to, if this model is correct about dark matter, this would not be found inside these mass ranges at 95% confidence limit. So you can have, for example, a dark matter candidate lying somewhere around, which our analysis was not sensitive enough. So the idea here is that you optimize your analysis, and you also have more data and sophisticated techniques so that you exclude a higher phase space, or you actually discover something. Now, so our contribution to the analysis, which was also published before previous version, is, you can see this gray band here. This is the previous result, and you can see that from here this exclusion limit has increased quite a lot. And yeah, this was this is the last result from mono Higgs BB in terms of 2HDM plus A, and it was published in 2021. You can find paper and more details in JHEP here. So yeah, this was a dark matter with mono Higgs for my thesis. Now, jumping on to the other plot you have here, this is a combination for all the searches in Atlas for dark matter with 2HDM plus A model as your interpretation. Here I show the same exclusion plot with capital MA and small ma, but here on top of Higgs to BB, for example this one, you have all these searches which are combined together. And this blue line, this green line here, shows the best possible result from Atlas on this search. So my contribution here is that, you know, like, you have all of these searches and they have different sources of uncertainties, right? So let's say you have an analysis where you have a lepton in your final state. You want to measure the PT, eta and masses of the leptons, for example, and then that measurement has uncertainty coming from the detectors. So these are called systematic uncertainties. Now, each analysis has hundreds of sets of systematic uncertainties possible, and they choose depending on what are their strategy for a specific analysis. So my task was to basically correlate all these uncertainties together so that we don't actually double count, or we don't eliminate a source of uncertainty that can actually impact your final results. And I also was responsible for taking care of the mono Higgs part that went into the final results. So here also, everything under this final curve here is excluded. And you can see that the impact that mono Higgs had. So if you see that the upper level of this plot, these are basically mostly coming from, the sensitivity is coming from mono Higgs. So for example, we could exclude up to 1600 GeV, and in the combination also we could only exclude up to 1600 GeV and so on. And the bottom part is coming from other combinations. So I mean, mono Higgs was the driving force behind this 2HDM combination result, which was also published last year in Science Bulletin, and it's also the first paper to be accepted in Science Bulletin from LHC. So yeah, this was about dark matter, and then I have one more slide to explain the combination a little more. So here we also, I mean, this is just, we saw the M scans, but there are also other parameters in 2HDM. You have the sine thetas, tan betas, and so on. We provide all the scans and to see if we can exclude all the other parameters, which you can find in the papers. Here I show the parameter scan for the dark matter mass m_chi versus the theory, the measured cross section compared to the theory, and all the dark matter masses under this area is basically excluded. So depending on the value of m_chi you choose, you can eliminate a theoretical cross section, for example. Okay, so that was all about dark matter. And before I move on to di-Higgs, I just wanted to show for fun how an actual data event might look like if you have a missing energy. So this was from the mono Higgs search, and here I eliminate basically everything just to be able to show you a clean picture of how an actual detector event would look like. So you can see here these cyan lines are basically your tracks, which are coming from VJets. And you have different jet algorithms, which basically from these tracks find these cones and try to associate whether this is coming from a Higgs boson or a W boson and so on. And this was one event where these B-tagged jets, which are coming from a Higgs boson. So this was one of the events which was part of the mono Higgs BB search. And this missing energy, I just draw it myself because you will not be able to see it. Okay, so now moving on to di-Higgs. So why di-Higgs is important, as I was mentioning at the beginning, is that it can give direct access to standard model precision measurement and also new physics. So what is it about? So we know that the Higgs potential has these trilinear couplings and quadric couplings, for example, these lambda values. And so far what we know is that at when you have the MH at 125, you have the minima of the potential, of the Higgs potential. That's all we know. We don't know how the total shape looks like of the Higgs potential and anything else about it, to be honest. So if you measure these lambda parameters, you can directly access this potential and actually map out how it would look like at different energy scales. So it gives you a direct access to self-coupling and Higgs potential, which is critical in understanding electroweak symmetry breaking. So as I said before, standard model predicts that this cross section is around 32.8 femtobarn at 13 TeV. So you measure these parameters and see if there is if you are matching with standard model or if something is new. Something new means you are exploring BSM di-Higgs again, where there are many models which can actually say that, okay, this production cross section is much more enhanced. So that means higher than standard model prediction. And there are also models which allows you to have different coupling constants than what standard model predicts. So this can also serve as a connection to dark matter. Why? Because let's say you have a resonance which can decay to a standard model Higgs, and you have another, let's say a scalar, which in turn can also decay to a dark matter candidate. So if you find these X particles or S particles, you have a lot of possibilities coming out from BSM di-Higgs. So now there are different types of di-Higgs production, and there are different strategies of how ATLAS handles these searches. So on your left hand side column, you have the non-resonant production. Non-resonant means that there is no sudden resonance of a new particle. All of these, for example, this is the gluon-gluon fusion. Then you also have different coupling constants. For example, this is a triple Higgs coupling, which is also called the K lambda. Then you have the a vector boson and a Higgs boson coupling is called kappa V. And also you have the kappa 2V, which is a coupling between two vector bosons and two standard model Higgs boson. Now these are all standard model diagrams, and basically here you are measuring the total cross section and also the kappa values if you can. For the resonance production, this is mostly motivated from BSM searches. You have new particles, for example, you have X and S, and they can have a vast topology and final states depending on what decay channels you choose. So the standard model prediction is that all these kappa values are 1. So kappa lambda, kappa V, and kappa 2V is 1. The goal is that either you measure these values and try to see if standard model is correct or not, or you find deviations. So as similar to the dark matter searches, in di-Higgs searches, it's crucial that you search for many channels. For example, you can have two Higgs boson, one going to two B quarks, the other one also going to two B quark. Then you also have one going to WW, one goes to BB, and so on. And these are the branching fractions of all of these different possible channels. And then depending on the decays of your bosons or other particles you choose, there will be multiple other topologies. So this is already a very vast, experimental signature existing, and the idea here is that you search for each channel, and then at the end you combine them to get the best results. Because since, as you have seen, that the total production cross section is around 32 femtobarns, right? And now if you have different branching ratios, that even goes lower. So there's no way that with the current data set you can have anything meaningful if you just do one set of analysis and try to measure these values. These are not statistically significant or sound enough to tell you correct measurement. So that's why we do all of these combinations to provide best results from ATLAS. Now, just to show some results from the non-resonant di-Higgs searches from ATLAS. So this was with run 2, so it's until 2018 data taking period. Here, just to not get confused with a lot of information here, so this tells you what is the maximum of signal strength you have. Signal strength means if you have, let's say, a new production, what is the cross section divided by the standard model. So let's say you have found a production where your cross section is 80 femtobarn, you divide by the standard model prediction of 32, and that parameter is called the signal strength. So on the left hand side columns you have different individual searches. So for example, this is missing energy plus 2 B quarks and 2 leptons. Then you also have multi leptons. Then you also have 4 B quarks. You also have BB and 2 photons and BB tau tau and so on. And at the very bottom you have the combined. So you can see that these numbers, the upper limit on the signal strength is actually decreasing for different channels, but also the combination gives you the best results. Why is it the best result? Because this is a non-resonant, where you are trying to see if your analysis matches the standard model. To match the standard model, your signal strength should be exactly 1. That means observed divided by standard model prediction is 1. So you have kind of said, okay, standard model is correct. So you can see that right now the latest ATLAS result is 2.9 sigma. So we are quite far away from standard model, but we cannot say that, okay, if there is something new or not. Why? Because we are not statistically viable enough. To claim that there is something new, you have to have 5 sigma or above. So far what ATLAS says is that the upper limit on the di-Higgs production cross section is less than 85.8 femtobarn at 95% confidence level. So that means that technically with the current data set you can exclude if there is a BSM di-Higgs. If there is a non-resonance di-Higgs, for example, it cannot be beyond 85. It has to be less than 85. So we are more inclined to standard model in terms of these non-resonant searches. So we also provide results on the other coupling constants, for example, this kappa lambda and kappa 2V. So here this plot shows the scan for the kappa lambda. So this star mark here is your standard model value, which is 1. And then you have theory prediction, you have the expected limits, and what you actually observe from different channels, and also the combined result. So the combined result for kappa lambda is that it's ranging from -1.2 to 7.2. So this is kind of in a way that's saying that, okay, we think that the range is between 1.2 to 7.2. Standard model says it should be exactly 1. So we're not sensitive enough, and we must look for newer methods to do data analysis, and also higher amount of data would help. And just to have a thought here, so this you can see if you follow how Higgs boson was discovered, this is kind of the similar pathway we are going through. So if you see like papers from 2000 before 2008 for Higgs boson discovery, the ranges were anywhere between 100 to 700 GeV. Now suddenly we found out in 2008 that it's 125, but you can see the analogy here that we are playing with different ranges here, and we're trying to improve these ranges year by year and try to zoom in on the standard model values if we can. Now this was with non-resonance, so you're measuring standard model. Now what actually does this results tell us? So as I said that the results show you that the total cross section cannot be beyond 85.8 femtobarn. We have a 2.9 sigma significance, and the slight deviation, which is almost more than twice the standard model, this is not enough for discovery because we are not statistically significant enough. So this could actually be a statistical fluctuation or a possible BSM signal. And for a possible BSM discovery with current data set, the signal must be more than 2 times standard model. Otherwise, we will not be statistically viable. So we're not saying that there is something new. We are also not saying that we are okay with standard model. What we are saying that there is a limit at which non-resonance production cross-section can go to. Now this leaves a question of whether really there is a BSM di-Higgs or not. And to answer the question, Atlas does BSM searches where you search for these resonance particles which can go to different decay modes and so on. And here is the latest result from Atlas where basically again the same strategy is maintained, where you combine different channels and give best results possible. So just to give you what to see in this plot here is that we don't see any excess. But you can see that at 1.1 TeV you have like around 2.1 sigma significance, which is of course not statistically viable, but it's still better than what we had before in, let's say, before 2018 and so on. So we are getting that, like we are having sensitivity to the BSM searches with the limited data, and hopefully with run 3 and High-Luminosity LHC we'll have more data, and probably we will exclude many more phase points, and if there is a new signal we can also observe. So there is a projection as well for what we expect, and I will discuss this in the later slides. So what am I doing in terms of di-Higgs searches? So as I said that we have multiple channels, and depending on the decay mode of what your final state are, you have multiple topologies and so on. So for example, I'm leading with another postdoc the run 2 and the partial run 3 Atlas di-Higgs searches in the BBWW channel. So this will include data taking from 2015 to 18 plus 2021 to 2024. So total about 300 femtobarns of data. And basically we are focusing on X to SH, where your Higgs boson goes to 2 B quarks always for all the channels, and then you also have 2 Ws where the W also can decay to hadronically, so you have 2 jets, or also to leptonically, where you have depending whether the lepton is inside the jet cone or outside the jet cone, you have multiple topologies. So there are different timelines of these analyses. So the most advanced is the 1 lepton boosted. So this is for run 2, which is going to be published in 2 months or so. And the rest of the analysis, these are all run 3 plus run 2, and this will have like 1 year time period for publication. But the interesting thing is that all these topologies are new, and there is no result so far from Atlas or for CMS in the mass range that we are scanning. So these results will be new, and this would be exciting to see how these come up, because Higgs to WW has around 34% branching ratio, and this has not been observed, explored. So it's a very exciting time for us. Just on a side note, for a personal note, that this is under a small, this is under an umbrella of larger Atlas group, and I have been nominated to be basically the leader of the group above, which supervises every di-Higgs search, including a B quark, C quark, or a lepton. Okay, so now with all of these limitations about data, statistics, and the results we have, what's next at LHC? That's the bigger question. So now this is the program schedule for LHC, and we are at the middle of run 3. So the run 3 data taking will go until Q3 of 2026. Then this round of run 3 which is 13.6 femto TeV, is over, then we'll have a long shutdown. Long shutdown means we will upgrade the detectors, we will upgrade the software and so on, so that we can prepare for the High-Lumi LHC, which will be 14 TeV, and it is expected to deliver 10 times more data than what we have so far. So this would be a lot of hardware and software development in the upcoming years, and we'll see how High-Lumi LHC progresses. Now, can we say something about High-Lumi, what we are expected to see from the current results we have, and if we can make projections? Yes, we can, and you can find more details about this here in this paper, but I'll slightly highlight some of the interesting things which we can actually observe. So again, standard model cross section would be between 30 to 40 femtobarn, because right now it's 32, and I think at 14 TeV it goes to, I think, a little 1 femtobarn more. So we are approaching standard model sensitivity in terms of predicting, in terms of verifying the standard model cross section. Significance, we are expected to have standard model significance around 2.5 to 3. So that means that now we say that, okay, the maximum cross section should be 85. With High-Lumi LHC, we will say that if standard model is correct, we will be able to say it at a confidence level of 2.5 to 3. But this is not guaranteed. This will depend a lot on how the systematics behave. Systematics means when we have the new detectors going in, all the new upgrades, how the uncertainties there are, if that goes fine or not. Then on the kappa lambda, the projection is that we will shrink the range from minus 0.1 to 3.6, and this will be a huge improvement from run 2 and run 3. Now the big question is, if all of these are true, what happens to BSM? So the idea is that if there is a BSM signal, can we see it in High-Lumi LHC? The question has two answers, and the first is, the exciting one is yes, but the signal has to have a cross section above 2 times standard model. So the BSM resonances, they must produce a signal cross section of around 70 femtobarns or more. So if there is a model which predicts, let's say, a BSM production cross section of 50 femtobarns, we'll definitely not see it in High-Lumi LHC. But if there is more, then it's possible. And possible means it should be possible at higher sigmas than 2.1, which we have. It could be around 3-4 sigma. But if we have higher cross section, it's better chance that we get a 5 sigma projection. So yeah, High-Lumi LHC will definitely give an answer whether we are more inclined to standard model, or there is indeed a scope for something else in terms of di-Higgs. So now the question is, okay, we'll have more data that will reduce a lot of statistical fluctuations and statistical uncertainty, which is a big concern in terms of these new BSM searches. But what else are we doing? Are we doing something to improve our analysis techniques? And one of the major developments that has been happening in Atlas is machine learning. So the idea here is that when you have an analysis which searches for Higgs to BB, the initial and the most fundamental task is to identify this Higgs to BB. If you cannot do this with good precision, your analysis will not give you good physics results. So in order to reconstruct these objects Higgs to BB, what happens is that you take the information of the tracks, the charged particles and so on, and you try to connect them to the originating particle, which would be a big problem in High-Lumi LHC. Why? Because we will have 10 times more data, we'll have higher luminosity. That means there are much more collisions, and there will be a lot of particles flying around with their tracks. So the difficulty is that it will be highly difficult to identify them in High-Lumi LHC because it's just too much. And the current data set and the current technology we have, it's impossible to have a higher efficiency to reconstruct these Higgs to BB. In other sense, even if you have more data, if you cannot identify, it's meaningless. You will not be able to do any analysis. Even the results could be even worse. So what is the solution? So what we are trying to do is train basically neural networks, which improves basically your object identification. So just to give you an example how far it has come. So here on this bottom right plot, you have the light jet rejection. That means so if you have a jet originating from a B hadron, we call it the B jet. If it's not from a B hadron, if it can be from a C hadron, we call it C quarks, and if anything else, we call it light jet. And it is very important that in a Higgs to BB search, you identify B jets and you reject other jets. So the sky line here shows the rejection of light jets, and you can see these different acronyms. These are basically different jet tagging algorithms over the years. So in 2017 we had something called Deep Learning 1, then you also have DL1R and so on. So don't worry about the jargons here. The point is that in 2017, if you want to identify a B jet, and let's say your baseline rejection capability is 1, fast forward 2023, with the same efficiency to tag a B jet, we can reject light jets 4.2 times better. So that means if you have a Higgs to BB one event, and if you have, let's say, Higgs to CC or Higgs to light jets other events, you can actually efficiently say 4 times higher that, okay, I have rejected the background, so I am actually able to capture the signal. So this is a huge deal. Why? Because if you roughly estimate the sensitivity or the significance is signal over square root of S plus B, right? So the more you reject your background, which is the B, higher is the significance. That means your analysis is becoming more sensitive to new physics. So this is very important for us moving forward in High-Luminosity LHC, and this improvement actually does a lot of good thing for physics searches in boosted regimes. Now, what am I doing here? So currently, as I said, that Atlas has moved on to this neural network based object identification efficiency, but the problem is that when we started this, we have a classifier for all. So you have a Higgs to BB classifier, you have a Higgs to CC classifier, and you also have a double hadronic and top quark and so on. So all of these are scattered. The problem is that when you have these scattered taggers, it's very difficult to use them in an analysis coherently, because let's say you have a Higgs boson, you also have a W boson, and then you are using 2 taggers which will have overlaps in between, and there will be also systematic uncertainties which can correlate to each other. And in neural network trainings, we actually don't know what's actually can impact your systematics. So the idea here is that we work on a unified tagger that would basically do the trainings all at once, and finally it will tell you whether it's a Higgs to BB or a top quark or a double hadronic or something like that. And the advantage of that is that you have less technical challenges moving forward. It's easier to explain and also easier to handle these different taggers, and it will reduce the statistical and systematic uncertainty which drives major uncertainties in BSM di-Higgs searches. So yeah, this we started a few months ago. This is still in the initial stages, but this would be an exciting thing to accomplish if we can actually deliver. Okay, so another thing Atlas has been doing is also improving the detector. So there are many components. For example, all the detectors in LHC are going through upgrades for the High-Luminosity LHC. So in Atlas there is a project called event filter tracking where I'm actively working on. So just to go, before I go into the details, I want to show how actually what is tracking means basically. So you have charged particles which are produced at the very center where you have the collision. Then the tracks fly out, and you also have this Atlas tracker which has multiple layers. So this is at the very inner center of the detector, and this is a cartoon showing how a reconstruction of a charged particle happens. So this charged particle, this black line, this is actually traversing through different layers of this tracker, and it leaves signatures there, and depending on the magnetic, depending on the momentum of that particle, it will have a bend, and you check the tracks and also momentum and everything, and that goes into your final object identification. Now the problem is that in High-Luminosity LHC this will be 4 times more difficult because you will have more events, and on top of that, since you have more events, your readout electronics has to be much faster to record all of these, otherwise events will be lost. So the solution for this is basically a trigger. What is the trigger? Basically, as I said at the very beginning, that since you cannot save all the events and you don't need to save them, you basically apply a set of selections so that you only select events which are interesting for you. So if you want to study anything to do with jets, for example, you will apply a jet trigger such that it will only store events with a jet, and so on. So there are multiple stages of Atlas trigger. So it's at the very beginning you start with 40 megahertz, and you go to 1 megahertz with the hardware It's called L0 triggers, for example, here. But not to go into too much technical details, basically this is just reducing the rate at which you store the events. The EF tracking comes in this stage where you have reduced almost 1 megahertz to 10 kilohertz. This event filter is supposed to help the CPUs. And the idea here is that you build this heterogeneous commercial system for LHC, and this will consist of CPUs, GPUs, and FPGA. FPGAs are basically your field programmable gate arrays, where instead of a pre-programmed CPU or GPU, you basically can have your own program and write on this little IC. This will basically read the tracks, for example, and decide whatever you want to do. So the idea here is that it will reconstruct the tracks in a better way, so that you can have better tracking and better physics results. So my involvement here is in the stage where this basically we are developing something called computer kernels. What do they do? Basically, you have a track, then in between you have these FPGAs, which are a little piece of hardware, but the FPGA will not know anything about what's coming in. So you have to tell the FPGA what to check for, right? So you put your algorithms through in FPGAs through a little piece of software. It's called the kernels. So then this kernel reads whatever's coming to FPGA. It tells FPGA what to do. It executes some algorithm in a parallel hardware logic, and then it sends it back to the CPU or GPU, depending on what you actually use. So the idea here is that you do a conversion from raw detector data to something that an IC can read, and then also convert then again that a CPU or a GPU can read. So for example, just to give a rough idea, it takes an event, for example the tracks, it executes some algorithm, and it outputs parameters such a way that you can do analysis for let's say physics objects. So this is pretty much a big bottleneck for Atlas right now, because without this there is no basically trigger, and without trigger we cannot do an analysis, or you have unlimited source of storage if you can, which is not possible. So this is an ongoing task, and we have been trying to decide which technology to choose. So for example, whether to choose a GPU or CPU, because CPUs are more cost effective, but GPUs are much faster. So Atlas will have a decision to make in few months, so we'll know what to do. But in any case, my work covers the in-between step, where we basically talk to CPUs and GPUs. Okay, so that already brings me to my summary. So for physics results, as you saw that for run 2 and also partial run 3, that we are working on a lot of searches, including dark matter and di-Higgs. So far we don't have any access, but we have stringent limits on both production cross sections and parameter space. We are also working on many methodological improvements, for example the neural networks, which significantly can improve object identification and signal sensitivity. We are also working on detector hardware upgrades, and also software upgrades that will enable us to take data efficiently for High-Luminosity LHC. And the goal of this is to have a new physics or better physics results in High-Luminosity LHC, which has a great, which can serve as a great opportunity to probe Higgs couplings, Higgs production cross sections, and see if there is any BSM physics or not. So yeah, my idea is to continue BSM searches and try to contribute holistically to the whole collaboration, and do meaningful physics. Thank you very much for your attention. Yeah. Yes. Yes. Well, we only so this is all lambda this one here. So Yes, but so I mean this is just to show the whole potential. We cannot measure this at LHC. Yes, this we can measure. Yes. So yeah, you basically break the symmetry and try to measure at minimum. Yes. Yeah. Yes. Yes. So I mean in terms of di-Higgs searches, we are basically if you do something in terms of a resonance, all we care at this point. Right. So in BSM physics, we actually don't measure any couples. All we are trying to see if there is an excess. Yes. So for standard model, we are at a stage where we just want to see. So if you see the results for individual kappa 2v, the statistics is not that good even for these spaces. No, not yet. We are still focusing on very basic studies. Yes. Yeah. Yes. Yes. Yeah. Yes. So maybe I can just slightly tell you what actually happens. So this is for the mono Higgs, right? Basically anything below 500 GB of MET, which would be, let's say, covering all of these 1200 regions, everything here should be your resolved. But I don't know in CMS how you define your resolved, because in our case this is all dependent on missing energy. On top of that, you have above 500 GB, which are mostly coming from all of these parameter space, and you can see that it's mostly covered by resolved. So yeah, it's above 500 GB MET of boosted, but I can discuss this tomorrow in more details here. Okay. Yeah. You mean the small a? This one. So okay, so this is in terms of 2HDM plus A, and also you have these final states, right? Higgs to be B is E2LL. If you go below a certain mass point, what happens is that, well, there is an analysis for this. These are Higgs to invisible decays. So you can actually have, yes, but you can have very low masses of dark matter, which comes from, because your Higgs is 125 and your small a has to be higher than 125, right? So if you go much lower, it will not give you that sensitivity, and those are basically covered by Higgs to invisible searches. So these kind of highly boosted regimes are not sensitive for those, so that's why you don't see scan range for that. But yeah, there are searches for this. Yes. Yeah. So this part is where, well, technically it is replacing the existing trigger, because it will not be fast enough for High-Luminosity LHC. But it's much more than that, because it also improves the tracking, because we need better algorithms to do the tracking, and the CPUs are not going to be enough. So that's why we have this intermediate FPGAs, so that we can reduce the load a bit on CPUs, unless you have you can do GPUs, which would be more expensive. That's why we're trying to explore how to not GPUs and to do a cost-effective way, so that CPUs can handle. So that's the idea. You have something in between, which is very cheap. Yeah. Yes. Yeah. So I mean, in High-Luminosity LHC, the whole atlas tracking will be changed in a detector. So now it is called ID. It will be an ITK, so inner tracker. So everything will be changed, and this is just a part of the big picture. Thank you.